This is, well, it's a bit lightweight, so I won't go into the extreme details, but it's part of the whole work that I also presented some months ago. We had a bioinformatics course in Dublin, and I'll give a very brief introduction of this whole thing that was presented over there as well. A bit lightweight, so we won't go into the details. I like this one. Act, think, work like a bit of a data scientist. The whole struggle in the GplusE project was really about that, trying to bring people together to have them collaborate, to have them exchange, to have them, efficiently, let's say, convert information into knowledge and work from that. So that was really the goal of our whole project. Let me see. Yeah, okay. So instead of diving into specifics, what I will do is introduce some concepts, tools, working patterns that really people like you who have followed these courses that you should get familiar with. Yeah. Before 2006, and I laughed with it this morning, I think, as well. Yeah. So statisticians were among the weirdest people in the planet, and then suddenly now everything is changing, and everybody says that the data scientist is the guy that we need. Now, I have performed a lot of analysis in animal science, and then typically you have case control studies, analysis of in vitro experiments, analysis of observational data, a lot of small data with typical test statistics. And now we go into the world of animal data sets that become very large, combining phenotypic and genomic data. This is a very challenging one. The real-time information that's coming in, batch data that needs to be combined, and then even unstructured data analysis which comes in. Right now I'm having some projects with deep learning on top of picture analysis. So you take pictures from animals, and what can you learn from that? That's something that's coming, the whole machine learning. The only thing what I think that data scientists in the animal science world need to do is they need to be able to understand the whole concept and then work with it with different approaches. And you will probably see that coming in a lot of studies, that people will also try to get students involved in that more and more. What has changed? In fact, nothing. The concept remained, a lot has changed, but the concept often remained the same. So don't be afraid about that whole data science, because the whole thing about data science is that nothing has changed, but it's just a new word for the whole statistics. So what's the difference between data science and statistics? Probably, if you look at Wikipedia, they will say it's an interdisciplinary field that uses methods, processes, and algorithms. Yeah. And to get insights from structured and unstructured data. Structured, they mean that it's organized in tables. Unstructured, you could think about information, for example, from files that contain something, but you don't know exactly what that is. That kind of concepts, that's around the unstructured part. This is the difficulty. It's really a lot of fields that you need to combine within the concept of mathematics, statistics, information science, even some computer science. Yeah, but this is the whole hassle. Many data science and big data projects fail. Yeah, and why? Because it's really a struggle, to manage it, because sometimes people have a certain level of understanding of what we're doing, and it's difficult to get that spread out. So it's really important in all next projects that we start thinking about that beforehand. Why do they fail? Yeah, that's the question, of course. To my opinion, it's really about knowledge transfer and trying to bring concepts to people so they understand and they can explore these concepts together. All right, what's the problem? This one I published some months ago. For this whole challenge is also there. If you look into, for example, simple welfare assessment, If you talk with people not in our industry, everybody talks about cow welfare, but it would be, imagine that all these cows that they have sensors, it must be easy to say, she's laying down 10 hours, this one is laying down 11 hours, this one 12 hours. It should be easy to get a kind of a metric that says this is good welfare, bad welfare. So far, people have talked about doing welfare audits, but to my opinion, that's useless, because a welfare audit is a one-time measurement. A herd is dynamic, a herd changes, so you need to have, let's say, almost a video of what the farm is doing to really get a good idea about the whole welfare. But question is, can this data work in trying to go towards an automated dairy cow welfare assessment? And we published this as a kind of a vision, not on as research, but a vision on what we need to do to go from the whole big data and data world into making useful things. So what's the issue in the dairy industry? This one is a big hassle. There is a lot of information coming from cows, precision livestock farming, diagnostic samples, there's local management software, there's milk processors that, or milk meters that have information. Everything goes to the cloud right now, and then we have phenotypes. Everybody's trying to catch all the data. Who owns the data? Big discussion. GDPR is there to bring another layer, to my opinion, of rubbish extra discussions. The only thing what's true is that the guy who owns the data is the guy who owns the cows. Yeah? And all the rest is rubbish. And we should stop talking about GDPR, and we should work with data instead of talk about data. So that's really my opinion. The delegated ownership is something else. You can pass your ownership to somebody else. You can say to Google, I don't care if you know my geolocalization, as long as you give me Google Maps back. That's delegated ownership. You give the localization information to somebody else. The algorithm that then predicts whether you will have traffic, yes or no, that's owned by Google, not by you. Yeah, that's how you work. You give something, you get something back. But people right now are stuck on this one. Is there really volume in dairy cows? The genotypes, yes. We started in GplusE working with the genotypes, and then you get into the gigabytes of data that come in that are really almost impossible to share amongst each other. If you look into the RNA sequencing, that's when it really gets big. Yeah. Then you go into the terabytes for some 100 cows. So to give you an idea, right now, the 1 gigabyte of data is enough for the DNA of 100 cows, but you need about 5 to 10 gigabytes for RNA-seq per cow. Why is that? Because this one is a specific density. Yeah, so they reduce the density, and then I always tell farmers, one stick is good enough for the entire genome of a cow if we would do full genome testing. But this is coming quick. In the United States, I think you almost pay about $10 right now for a full for a specific SNP test, and it's going quick. I think a lot of animals will be genotyped. How do you store it? How do you process this data? How do you share it? I hate it when people start sharing sticks. It's not, which version do you have? I don't know. I forgot about it. Now, the velocity is also something challenging. This is not in the GplusE project, but in Kentucky, there was a professor at a certain moment, and they installed almost every sensor that you have on cows. They installed on their herd. They have about 200 animals. They have 4 pedometers. They have the accelerometer here. They have the sensors in the ear. I think they have about 20 devices on each cow. Yeah, they have the problem that some cows don't have ears anymore because they had so many tags in it. But this goes very, very quick. This is incredibly fast. This one is another problem that occurs. There's only one part in Europe which is well organized, and that's where Søren lives. That's in the Nordic part of Europe. All the rest, the data is extremely scattered. There is databases that are totally different. People call diseases different. Yeah, we implement it different, and this really holds us from analyzing the agricultural data in a proper way. This is a very, very big challenge. And then on top, we have different people, we have different budgets, we have different statistical programming languages that we understand. Even just understanding each other is a challenge. Yeah? And this is what we need to do. Work on that variety and respect it. We have on-farm, off-farm data, I explained. There's a lot of veracity in data, noise, abnormality, but it's rarely reported in animal science. If you ever submit an article and there's a reviewer that asks, give me something about your data quality, it's me. I will tell you, every review that I do, I always ask people, tell me which animals you dropped. Why did you drop them? Because those are the sick ones. I don't want the study design with only healthy animals. I want the study design with the animals that are really true. Animals calving twice a week, it happens in a lot of farm management software. Before you want to use animal management software, you need to be aware of that. 20% of the animals is misidentified in the United States. There's a white cow that calves from a white calf. There's a black one and a black calf. Mother and daughter, that one is black, probably it's this one. If you have 20 animals calving in one pen, what?
And there are lucky guys.
Yeah. But on the other hand, this is changing now because we have the genomics. Via the genomics, you can do some parental check. So, and in the Netherlands, for example, they reported that it's only 5%. Everywhere in the world where you see that there's an ear tag number, which is official, that changes quite quickly. We did some review about people in dairy science, whether they are so honest that, for example, they do a publication, but in the material and methods, you find, yes, but we had an issue with the data, and this is what kept us from doing specific things. And we started looking whether people honestly mention that. And to give you an example, between 85 and 90, there was one publication that reported that. But let's be honest, all of us, we struggle with that. The first thing you have to do is you have to clean it. But that's valuable. Yeah. But what you clearly also see is that the moment that people started mentioning it more often, between 2010 and 2014, where do you see it? It's in the disease articles. What do we all want to do? We want to get rid of the disease in the cows, but that's where the data quality issues really occur. So we need to be aware of that this is really a challenge. Getting rid of the diseases will require us to respect that. This is a bit too detailed. This is reality. And I deliberately took one. I deliberately took one from the Netherlands. Our friends from the north, we always say. But this is reality. It happens. People making the mistake. But it happens, and we need to be working with that. At a certain moment, what we did is Christophe and I, we worked on a random forest technique to see, can we predict if data that comes in from a herd, from a farm, whether we can use it, yes or no, and if we can find methods to clean it up before it gets analyzed. Random forest predicts data quality. So to give you an idea, one of the most important things, if you study farm data, so not, let's say, research data, but farm data, you need to be aware that if the animal is not born on the farm, the quality of the data drops quite quickly. If they acquire animals, they have a limited amount of data that's there, so that needs to be, you need to understand that these animals might mess up your data. And so we looked at different parameters. This is, again, you see, this is a ranking. So the random forests ranks the different features according to their relevance. So the most important one was there. To give you an idea, we also looked at whether the software underneath the data was using a relational database. So a relational database means that there is something which has keys and numbers and that, but that didn't affect it very much. Even the correct check digit. So normally in Europe you have a number, an ear tag, and then the last number is a check digit. It's like your bank account. It checks whether you did the right input. Well, it didn't really matter to our data set. So these were the ones that were most important to our study at that moment. So that's the challenges in the different in the data set. A little bit about computer science, and after this one I think we should stop. But the history of computer science for some people, I like this one. If you have a bit of music, It's more fun to compute. It's a song by an electronic group from Germany, Kraftwerk, one of my idols. They talk about this already in the 80s. We have RAM, ROM, CPU. So your computer has something which is called RAM, which is very, very, let's say, volatile memory. Yeah. So your CPU, which is the processing unit, so that one is doing the calculations. It spits it back to something which stores it in a volatile way, and then you can somehow store on let's say, a disk and spread out, for example, a file towards some memory that's not volatile. Yeah. What has changed over the last years is that the cost to, and this is my excuse for the bad maybe I won't do that. The cost, yeah, to store something in memory, yeah, has decreased enormously over the last years. Yeah, and just because of that, yeah, we also in the meantime had a number of transistors per physical unit went up, so our computing power is going up incredibly. If you look into this one, this is especially also in animal science. I don't know if some of you have been playing with hardware, but to give you an idea, this is an Italian project by students, and this is hardware that you can buy for €10. What can it do? This can do computations. You can put a sensor in it and add it to a cow. I have seen cow projects based on this kind of devices. People do it open source. People, I have no idea why, they do it in their free time. Normally people have to be paid to do things. In the open source community, everybody does things for free. I don't know why, but it happens. So open source hardware is very popular. Arduino is the Italian project. You might know Raspberry Pi. This is a Pentium 2. If you remember from your old days, right now, this costs, you see, yeah, the Raspberry Zero is €10, and you have an entire calculating power device. People are making projects, and this is going very fast. And it creates a lot of extra data, and we don't know where it will end. Moore's law, some might know it. Gordon Moore was somebody working at Intel. What he said is that the speed at which we are creating new and more powerful computers that have the possibility to do the analysis is almost tripling every 18 months, so every year and a half. So but you won't be able to read it, but I'll tell you which one it is to give you an idea. This is where the Pentiums, yeah, the IBM 386, 486, then Pentium 1 came, Pentium 2, and they see that the speed, yeah, was increasing every 1.5 year. Right now, computer science is moving even further. To give you an idea, at this point, people got stuck. In 2010, people got stuck. And then you saw two things happening. There's the HPC world, high-performance cloud computing, or high-performance computing. They try to go even further. They try to go really, really into a world where transistors become, yeah, almost in an, yeah, I don't know how to express it, but in a nano world, yeah, where Google tried something else. What did Google do? Google tried to scale up horizontally. So they started to go this way. So they kept using the old machines, but they parallelized them in a cluster. That's the difference between the two worlds that's going on. And even you need to understand that genomic analysis is going this way. They're going entirely HPC, but in the humans, they all go parallel. Genomic analysis in humans is all parallel. In animal science, it's all HPC. I'm looking right now into trying to find a way to also do the human way in animals. It's fascinating how quick it's going. Future of software languages. Every 3 years, there's a new language which comes up. Honestly, I don't know where it will end. Python is extremely popular. R is popular. R is not good for big data science. Now there are some movements to make R also for big data science good. Python and Scala are the things. SAS is dead in my opinion. SQL is something that you should know, but use it limited. But this is going so quick, it's almost difficult to find out. But the good thing is you can learn it very easily online. The history, to give you an idea, there are maps. People have made maps. It's a bit of a nasty drawing, but people have made maps on showing in the early, I think this is 30, no? 57, this is 57. There were 2 languages, and all these languages, people started creating their own versions, and people had their own vision on how to do it, and eventually now we are somewhere over here. It's quite difficult to follow, but there are different languages, and they each have their application. I don't think the YouTube will load. This is how Python was built. Python was built by one guy in the 90s as an evening project. Yeah, and then people started to commit. So every time that you see something happening, yeah, you see, this is when somebody added a piece of code. Open source, nobody owns it. It's worth millions and millions of money, and it's open source. Everybody can use it. You can look for this video for almost half an hour, and then you will see Python 1, Python 2, Python 3, and how people have built this in an open source community. It's fantastic. It's nice to see, but this is probably how also in other pieces of industries we will start to work together. In an, I don't know, open source pieces in open source. But to give you an idea, Microsoft has tried to really grab on this because they hate it, that there's suddenly something open source that they don't have a hands on. But somehow people did it. Somehow people worked together and they did it. This is also something that's challenging to think about how the future will look like in some years. But this is nice to see, no? Trends. Which language should you learn? Right now, you can see Python, R, Java, then still the C++, Scala. If you look into the Scala one, the new kid on the block, this one is very recently improving. I write a lot in Scala because it scales. That's the idea. Don't forget the popularity is also important because if it's popular, then there's also a lot of things on Stack Overflow. Stack Overflow, you might have seen, if you have a question, then somebody has already done it. So what you see is that if you know Java or Perl or Ruby, R, I don't like to see this. Yeah? This is the popularity rank on GitHub of R, but there are more questions asked about it. So there are some challenges. What you like to see is that they line up over here because then it goes on with a lot of projects, but not too many questions. So R has to do something about it. But to give you an idea, there's already more Scala projects, and Python is here. You see? A lot of projects in Python, but a lot of tags on Overflow. Good news, MOOCs. Coursera, if you want to learn a new language, Google it. Coursera, you can learn almost in some weeks a new language. Somebody has built an open course. Normally you have to come here and to do it via this kind of courses, but people all over the world have offered free courses. Sometimes you can pay a little bit of money, and with that money you then get a certificate that says this person now has an official Python license or whatever it means. The software, the same problem. This was the big data landscape some years ago. Now it's here. It's really challenging to find out which one is popular, which one is not. For those who have heard about the name Apache, follow it. It's an open source foundation. Once you get the stamp Apache, then it's a kind of a way that people acknowledge that a lot of people have contributed to this project. There is some rules about it, and then they will help having that project lift to a next level. This is going very quick since 2000. So in the early 2000s, there were a very limited number of committers, yeah, and then and projects. But now this is going very fast. You can look at it. To give you an idea, the entire database, for example, of Facebook is open source. How they build it, that's open source. Yeah, Yahoo, they have some projects on there. It's really interesting to see, and it's nice because people collaborate in that idea. And normally I have some stuff I think going on beyond this, but I don't think it's. Let me see. How much time did we have left? Minus 2 minutes. Well, then I stop. I had some tools ready that I use a lot, but a bit of an end. Good. We'll have dinner.
Thank you very much.